I've been requested to do a ladder rate of change problem, and I figure I would do one because it really is the classic rate of change problem. And it's part of any complete calculus education. So what is the ladder rate of change problem? So let's say I have the ground, and I will do the ground in brown. Let me see where I'm going to draw my wall. See, this is the ground. That's too thin. Let's see, this is the ground, a thicker ground. That's the ground, and then I have a red wall. Oh, this red's a little yellow wall. This is my yellow wall. And then leaning against that yellow wall and the ground, I have a ladder. I have a ladder. So this is the ladder. I'm looking at it from the side. That's my ladder. I'm just looking at the side view of the ladder. This is the wall. This is the ground. That's a ladder leaning against the wall. And let's say that my ladder is 10 meters long. 10 meters long. So and let's say that for whatever reason I've kind of greased up this wall and the floor here, and so a normal ladder would just kind of stay where it is, but especially because this floor is all greased up, the bottom of this ladder is moving to the left. So let me draw that. Let me draw an arrow. So the bottom of this ladder is moving to the left. And let's say it's moving to the left at 4 meters per second. 4 meters per second. So let's think about a couple of things. What's happening? And let's when this point right here is moving to the left at 4 meters per second. As long as we have some height here, at some point this whole thing's going to fall down, and the ladder, for whatever arbitrary reason, will just be it'll just be sliding along the ground. Maybe someone's pulling it or whatever. But before the ladder completely falls to the ground, while this is being pulled out this way, this point right here is going to be coming down, right? Think about it. It's just going to be, in fact, that's probably what's causing it to slide to the left. And actually, it'll do it at an accelerating rate. And we're not going to worry all about that. We're just going to do the classic ladder problem. But I just want to give you the intuition that if you were to, if you were to put a roller here and put a roller there, that's what a ladder would do. It would slide down. And when it slides down, this point would go to the base of the floor right here, right? This point would go down. And this point would go out to the left until the ladder is until the ladder is like in something like this position. Until it is flat on the ground. I'm just doing it right below the line, right? And at that point, it would either stop, but if someone's pulling it, then it could continue to go at 4 meters per second, whatever. So hopefully you're satisfied with that. So my question to you is, at what is the rate of change of this point, of the kind of top of the ladder? What is its rate of change downwards when the left point of the ladder right here is going to the left at 4 meters per second, and this distance right here, let me see, let me do it in a different color. This distance right here is 8 meters. And actually, let me do the mirror image of that, just because I don't want to use negative numbers and all of that. I just realized that so let me just draw it really messy real quick on this side. So that's the ground, that's the wall. I'll do the ladder in a different color still. That's the ladder, it's 10 meters. This point right here is moving to the right at 4 meters per second, because I'm going to do the horizontal component as x, and I wanted this to be a positive x value instead of a negative x value, so that's why I did that. We're 8 meters away, so it's positive x, right, if we take this 0, 0. And what I want to figure out is the rate of change of this point of the ladder, the top point of the ladder. Let me do that. How fast is that moving down, right? So how do we think about this? Well, let's call this distance right here, let's call that distance x, because it's kind of the horizontal displacement. And let's call this distance up here y, right? So at any given point in time, how does x, y, and 10 relate? Well, this is a right angle, so we can use the Pythagorean theorem. So we know that x squared plus y squared is equal to what? It's equal to the hypotenuse squared. It's equal to 10 squared, which is equal to 100. So this right here describes, if you watch the video on implicit functions or implicit differentiation, this is kind of an implicit function of x and y, right? Or an implicit function of x, really. So what can we do now? Well, we're dealing with rates of change with respect to time, right? This is 4 meters per second. This is the rate of change, or this 4 meters per second. This is the rate of change at which x is changing with respect to time, right? That's dx dt. How much does x move in a very small amount of time? And what are we looking for? We're looking for how fast is this y value moving downward, right? So we're looking for dy dt. That's essentially what the question is asking for. How fast is y changing as a function of time when x is changing at a function of time at 4 meters per second, and x, the value of x, is equal to 8 meters. So I know that seems very complicated, but essentially all we do is we take the derivative of both sides of this equation with respect to time. So let's do that. So let's take the derivative with respect to time of x squared plus y squared equals, and we have to do it to both sides of this equation, to 100. So what's the derivative with respect to time of x squared? Well, it's the chain rule. It's the derivative with respect to x of this entire expression. So that's 2x times the derivative of x with respect to time. That's just the chain rule. Plus the derivative of this expression with respect to y. So that's 2y times the derivative of y with respect to time. And if you found this to be a little confusing, you might want to watch the video that I actually just did on implicit differentiation. It gives a little bit more intuition why this really just is the chain rule. But hopefully you get this a little bit. And then how much does 100 change with respect to time? Well, this 100 value is never going to change because, frankly, the length of the ladder is never going to change, right? That's where that 100 comes from. It's 10 squared. So the rate of 100 with respect to time, well, it never changes, so it's equal to 0. And what do we know? We know x, right? We know x is what? X is, at this point in time, is 8 meters. We know the change of x with respect to time is 4 meters per second. Do we know y? Well, I think we do. When x is 8, what is y? Well, we could just use this formula right here. We have 8 squared plus y squared is equal to 100. So 64 plus y squared is equal to 100. Or y squared is equal to 36. And we know, so y is plus or minus 6, but we know that we're only dealing with positive values in this, at least in this example right here. So y is equal to 6. So we know x, we know the rate of change of x versus time. That was given in the problem, 4 meters per second. We know y, so then we can solve for the rate of change of y with respect to time. So let's do that. Let's just substitute the values. So what's x? We're saying, well, what is the rate of change of y with respect to time when x is 8? So we get 2 times 8, that's x, times the change in, so this is 8. What's the change in x with respect to time at this moment in time? It's 4 meters per second. That's 4, so 2 times 8 times 4. Plus 2 times y, we just figured out that y is 6. So this is 6. So 2 times plus 2 times 6 times, and this is what we're solving for, dy dt is equal to 0. So what is this? 2 times 8 is 16. 2 times 8 is 16 times 4 is 64, right? So 64 plus 12 dy dt. And let me erase some stuff. I tend to try to crowd too much into one window, making things confusing. Actually, we've actually already drawn that, so let me erase my, whoops. I think that is good enough. Okay, so then we can simplify up here. So let's just, that equals 0. Subtract 64 from both sides, we get 12 dy dt is equal to minus 64. And then you get the change in y with respect to time is equal to minus 64 over 12. And what's the greatest common factor? I think it's a 4. So that equals minus 16 over 3. Right? Or that you could say that's 5 1/3 or 5.3. And it's going to be meters per second. That's the units. So the change, let me write it that way just so, is equal to minus 5.33. I mean, you could whatever, meters per second. And there we have it. And you might say, hey, why is there that minus there? Well, it makes sense because while the x value, its rate of change with respect to time, it's going in the positive direction, right? At least the way I drew it here. The x is going to the right, so its change is positive. But what's happening to the y value? The y value, you could say it's velocity, right? Its velocity is downward. So that's where that negative value comes from, because it has a negative velocity. I mean, really, this is kind of just the x and y velocities of those different points. And you can think about it a little bit that the x, at least at that point in time, while the x value is increasing at 4 meters per second, the y value is moving even faster downwards. So that's something to think about. But you might want to experiment with it at different points in time, because it's going to be dependent on where we are. And kind of at what does the right triangle look like. But anyway, that is the classic rate of change problem, the ladder problem. I will see you in the next video.